right, welcome back. We're now going to be talking about a very special version of the normal distribution called the standard normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1. That is always true. The reason why this specific distribution is so special has to do with the history related to probability and statistics. So a long time ago, let's say somebody wanted to determine a normal probability by determining some area under the curve. Well, every time somebody wanted to do that, they would have to use a lot of sophisticated calculations and it would take a long time. So somebody came up with the bright idea of creating what is called the standard normal table. And you should have been able to download a version of the standard normal table from our D2L shell before you started watching these videos. If not, you could go back, pause, and go get it now. But what the standard normal table does is it takes the area under the curve from negative infinity up to some value of x. And it does this for lots and lots and lots of different values of x so that people can know the probabilities under the curve, specifically for the standard normal distribution. Now you might be thinking to yourself, that's great and swell and all of that, but what about all the other possible normal distributions out there? What if the mean isn't 0? And or the standard deviation isn't 1? Well, we have a solution for that problem. First, we have to create a special label for random variables that are standard normals. And the label we have chosen is the z. So if you see z as a random variable, it's a standard normal random variable. So what we now know is if you have a random variable x and it follows a normal distribution with some mean mu and some sigma standard deviation. Just by taking x minus mu divided by sigma, you are now creating a random variable that is distributed normal with mean 0 and standard deviation 1. In other words, we can transform any normal random variable into a standard normal random variable. And any value of x can be transformed into a z-score by taking that value minus mu divided by sigma. This is a pretty cool, pretty powerful thing we can do. So what this means is that if we have a standard normal table, we can look up probabilities for any normal distribution we please. So if each data value of a normally distributed random variable x is transformed into a z-score, the result is the standard normal distribution with a mean that's 0 and a standard deviation that's 1. Now I've crossed those two out because that mu and sigma are different than your original mu and sigma. The idea is that you have a normal distribution, a random variable x following a normal distribution with a mean mu and a standard deviation sigma. Then you create z by taking x minus mu divided by sigma, and that z is now distributed normally with mean 0 and standard deviation 1. What this means is that we can use the standard normal table to find the cumulative area under the standard normal curve, and we can translate back and know the area for any normal distribution. So let's learn a few more properties about the standard normal distribution before we move forward. First thing you should know is that most of the action for the standard normal distribution happens within 3 standard deviations of the mean. So as soon as we get down to z equals negative 3.49, roughly negative 3.5, any area under the curve is really minuscule, very close to 0. So we're not going to worry too much about values below this because basically if we were looking for areas under the curve in this area, we would get something that's equivalent to 0. Another fact to understand is the cumulative area increases as the z-score increases, and that makes sense, right? If my z-score is negative 1, I'm taking the cumulative area up to that point. Well, clearly, if I keep going, I'm only going to be adding more area. So if I go all the way up to 0, I've added up a bunch more area. If I go to 1, I'm adding even more area, and so on. Because the standard normal is symmetric around 0, 50% of the area under the curve is below 0. 50% of the area under the curve is above 0. So this area from negative infinity up to z equals 0 is going to be 0.5. Half of the probability lives down there. And if we were to keep accumulating probability up to z equals 3.49, we basically have covered almost all of the probability. So the area under the curve altogether from negative infinity, which is that way, to positive infinity, which is that way, is 1. But what we're basically saying is it's close enough to 1 when you get to z equals 3.49 that if we have values bigger than that, we're not even going to worry about it too much. We're talking about infinitesimal amounts of probability above z equals 3.49. So this is the point in time when you should get out your standard normal table. So we're going to start doing some problems and practicing some concepts that you're going to see in your homework. So as our first problem, we're asked to find the cumulative area that corresponds to a z-score of 1.15. Now when it's asking for a cumulative area, it's basically asking us for the area under the curve from negative infinity up to whatever the z-score is. So that's what we're looking for. So we're going to get out our standard normal table, and we're going to look for 1.1 along this first column, and we're going to find it right there. That corresponds to the 1.1 in the z-score. And then we're going to go across the top until we get to the 0.05, and that's going to correspond to that last digit. So we find 1.1 in the left-hand column, we find the 0.05 in the top row, and then we go across that row that says 1.1, and we go down that column for the 0.05 and find the value where the two intersect. And that's going to be our area under the curve up to z equals 1.15. And in this case, that area is 0.8749. Now let's give you a chance to try this. I want you to find the value in the first column that goes with negative 0.24. Notice that we're using the other half of the table this time. Did you find it? If you found it right here, that's correct. And now we need to deal with this digit, and we're going to do that by looking right here. And where those two intersect should be the value we are looking for. So there's the negative 0.2 in the left-hand column. There's the 0.04 in the right-hand column. And if we follow across that row and that column, we get to 0.4052, and that is the area under the curve up to the z-score of negative 0.24. And remember that area under the curve corresponds to a probability. So what's the general procedure we're using here? Well, the first thing we're going to do is sketch the standard normal curve and shade the appropriate area under the curve. And we just are going to do that to make sure that we're doing the correct thing as we go. It's always good to have a visual. The next thing we're going to do is find the area under the curve by following the directions for one of three cases. So for case A, we're going to assume we're trying to find the area to the left of the z. And that is the easiest case, right? Because the cumulative probability starts at negative infinity on the way left and goes up to whatever the z-score is. So we're going to use the table to find the area for that z-score. And the area to the left of z equals 1.23 in this case is 0.8907. So we're all set. Now, in the second case, the B case, we're asked to find the area to the right of a z-score. And we've got a little problem because our tables are not set up for us to do that directly. But then we remember the complement rule. Yes, we learned it in our probability section of this course, and it's important. So what we're going to do is find the cumulative probability up to 1.13, and then take 1 minus whatever that cumulative probability is, and that's going to give us the probability that goes above that z-score. And if we go and look at the table, we see that the area to the left of z equals 1.23 is 0.8907. So 1 minus that value is 0.1093, and that gives us our probability to the right of that z-score. Finally, what do we do in the third case when we need to find the area between two z-scores? Well, what we're going to have to do is we're going to have to use our standard normal table twice. The first time we're going to look up all the cumulative probability up to 1.23, but we've overshot it, right? What are we going to do about this section here? Well, we're now going to get a second cumulative probability up to negative 0.75. And if we subtract out that second section, that's going to leave us this area here, negative 0.75 and 1.23. So we know that area to the left of z is 0.8907. We can look up the area to the left of negative 0.75 and find that it's 0.2266. Perform our subtraction, and we end up with an area under the curve between negative 0.75 and 1.23 of 0.6641. All right, let's give you a chance to try it. So I'm going to give you a little bit of time for you to take a look at your standard normal table and see if you can find the area under the curve to the left of z equals negative 0.99. Okay, did you find it? If you got the value 0.1611, then you found it. You used your standard normal table correctly. If you didn't find that, go back, try again. Okay? Here's a second example. What about the area to the right of z equals 1.06? So remember, if we're drawing our curve, now we're talking about an area to the right of it. Remember which case that was and what we need to do. Give it a try. Okay. If you were able to look up the area to the left of 1.06 and find out the area under the curve is 0.8554, and then if you subtracted 1 minus that value to get 0.1446, then you did this problem correctly. Congratulations. Here's one last example. Let's do this one together. We're going to find the area under the standard normal curve between z equals negative 1.5 and z equals 1.25. Ready? Well, that's the area we care about. So the first thing we have to do is look up the cumulative area to the 1.25, and we find that that's 0.8944. And then we need to subtract out this section, and we look up the area that goes up to negative 1.50, and we find that it's 0.0668. Subtract 1 from the other, and we get a final answer of 0.8276. So what we're saying is that the probability that a random variable z would fall somewhere between negative 1.50 and 1.25 is approximately 0.8276. All right, that is our introduction to the standard normal distribution. You should go off and try the homework now, and I'll see you for the next set of lectures.